So thank you everyone for kindly joining us for today's lecture during the celebration of the International Medical Physics Week, kindly organized by the IOMP, or International Organization for Medical Physics. Today we have two wonderful speakers that will be talking about the Geant4 project. That is a software that is very important for Monte Carlo calculations of particle interactions, both for perhaps with applications in radiotherapy as well as in imaging. I would like to ask all the participants, as is customary, to mute your audio and switch off your video in order not to reduce the bandwidth. And also kindly, during the presentation, please write your questions and answers, to Q&A button on the bottom of your Zoom screens. And I will read your questions at the end of the presentations. I will share my screen now. Magdalena, can I share screen?
Yes, sure.
Thank you. And it is my pleasure to firstly invite Associate Professor Susanna Guatelli from Australia, who will be talking to us on Geant4 for medical physics applications and will give us an overview and the latest updates. Susanna is actually a leading international expert on Geant4 Monte Carlo code for medical physics applications, and she has been working in the field since 2002, and she's also a member of the steering board of the Geant4 International Collaboration in her role of coordinator of the Geant4 Advanced Examples Working Group. She also leads the Geant4 Medical Simulation Benchmarking Group, dedicated to the systematic testing of Geant4 for medical applications. Over to you, Susanna. I will stop sharing.
Thank you very much, Eva. I will share screen. I will share my screen.
Beautiful, we can see it.
Okay, now it should be fine.
Excellent.
Okay. Thank you for inviting me. It's an honor. It's my 20th year of career in medical physics, so thank you very much. Let me acknowledge the traditional custodians of the land on which Wollongong is built, the Darawal country, where I'm doing my talk tonight. Geant4 is a general purpose Monte Carlo code modeling the particle transport and interactions with matter, and it's developed and maintained by a large international collaboration counting more than 100 contributors. Geant4 nowadays is extensively used in medical physics applications to verify clinical treatment planning systems, to develop quality assurance detectors, it's used for imaging, to study the radiopharmaceutical production in nuclear facilities, and also in radiation protection applications. On the right, you can see this plot that shows the number of publications per year in PubMed of Geant4 and other general purpose Monte Carlo codes, and you can see that the use of Geant4 in the years it increased a lot more. So with Geant4 it's possible to perform studies in the field of dosimetry, microdosimetry, study the DNA damage. I will not talk at all about DNA damage because we have Sebastien, so I will focus on other applications of Geant4 in medical physics. Geant4 then can be used, let's say, as a standalone Monte Carlo, but there are also the platforms of Gamos, Gate, and Topaz, which can be used that can facilitate the use, an easier use of Geant4. Here I will focus on Geant4 itself. To learn to use Geant4, it's required a basic knowledge of C++ and object-oriented technology. There are usually schools and workshops. I usually run a school at the Uni of Wollongong every couple of years. I had to say that with COVID had to slow down, but please keep an eye on the website of Geant4 where our schools and workshops are advertised. Then we have a website with the documentation, where we have the installation guides, the user's guides. The user's guide really indicates and gives information on how to develop a Geant4 simulations, and the physics reference manual that summarizes the physics models used in the codes. We have many examples to support the users, from basic to advanced. The basics examples guide the beginners to learn to use the fundamental functionality of Geant4. Then there are the extended examples that show the use of Geant4 show very specific functionality, while the advanced examples show the use of Geant4 in more realistic applications, including medical physics. There are Geant4 user and technical forums. Here on the right, you can see the screenshot of the Geant4 forum where users can post their questions, and usually these questions are answered within 24 hours. It's very important to learn Geant4 in my point of view. Let me say for the research activity, but let me now speak a little bit in my role of lecturer. Well, it's a very important, especially in medical physics, where this field is requiring more sophisticated computing skills. It's important for the students to learn to use Geant4 and understand the basics mechanisms that underlie this Monte Carlo. So I really encourage, especially the students, to learn to use directly Geant4. Now I will give you an update of Geant4 in terms of physics capability and physics validation, important for medical physics, and some updates on the Geant4 examples that may be of interest for this community. This slide summarizes the Geant4 physics constructors and list for electromagnetic physics. When we want to develop a Geant4 simulation for medical physics, you want to model the electromagnetic interactions. Well, we provide some already pre-built physics constructors. This table shows the main characteristics of these physics constructors. And let me just focus a little bit the attention on this option for physics constructor that has been built specifically to provide more accurate results. And this is of particular interest for medical physics applications. For what concerns the hadronic physics, here I show to you some physics processes and models of interest for particle therapy and radiation protection. So for proton therapy, we have the binary cascades. That models the binary cascade of protons, neutrons, and pions. Then the alternative is the Bertini cascade. We have the heavy ion fragmentation that can be modeled either with the QMD, the binary ion cascade model, or the ICL. Then the binary cascade activates the pre-compound model, which then you see finishes here at low energies with the nuclear de-excitation. Geant4 has some high precision data libraries for we use a lot in medical physics, the ones for neutrons, because they model more, this data library models more in detail the interactions of neutrons below 20 MeV. And Geant4 has also the capability to model the radioactive decay that is also very important in our field. I will comment now on some new features of the Geant4 11 release that was yes, it was done in December 2021. This is a major release, which means that there are major changes in the codes. All the changes are listed in the Geant4 releases notes that accompany Geant4. Here I will summarize some of the most important changes of also interest for medical physics. First of all, we have a multi-threading at the level of the events. And this is important to have a better computational efficiency. We have a better efficient, a better management, more efficient management of the physics processes. Now it's possible to activate the gamma linear polarization on top of the electromagnetic gamma physics in all the electromagnetic physics constructors. And this is important if you work with the synchrotron radiation. And we have also a new model, the so-called G4 low-P physics that is meant that describes low energy polarized X-rays transport in Geant4. Now there is also a model that describes the quantum entanglements in positron annihilation. This may be enabled and may be used in, for example, in positron emission tomography applications. Concerning the photon processes, the big development that has been done by Michelet with the student Lee and with the Sebastien is the implementation of the EPICS 2017 cross sections for photons, and now are available in Geant4 and can be used. We implemented a new data library modeling the atomic excitation and pixie. This data library has been provided as an alternative to the default one, and the characteristic of this data library is that it relies on the Artrefoc approach, which is recognized to be more accurate. We have a new ionization model that has been released, the G4 Lienard Sorensen ion model. And then there are also important developments in Geant4 DNA, but again, this will I will leave this to Sebastien. Concerning the hadronic physics component, the new IAEA 2018 data library for gamma nuclear cross sections has been included in Geant4. As we have in Geant4, we try always to improve the physics models, and it's very important that we monitor how this physics improvement and physics changes impact the physical quantities of interest for medical physics simulations. This motivated the creation in 2014 of the Geant4 Medical Simulation Benchmarking Group that I'm coordinating since 2014 with Pedro Arce of CMAT Spain as Deputy Coordinator. This effort includes the contribution of 45 researchers from 29 institutions of 12 different countries. And nowadays we have 20 tests where we benchmark Geant4 physics list for medical physics applications against the reference data and experimental measurements. These tests are executed regularly on the CERN computing infrastructure for regression testing. with the goal to provide the physics list recommendations for users and to monitor the physics capability of Geant4. You can access directly the results through this Geant4 validation portal. You can download the results of the regression testing of Geant4. We've done our first publication in medical physics, where we documented this work for Geant4 10.5. We confirmed that the Geant4 IM standard physics option 4 is recommended for accurate simulations in medical physics, and that this hadronic physics list, the binary cascade with HP data libraries, provides a good overall description for proton and heavy ion therapy. The test span from fundamental physics quantities like photon attenuation coefficients, electron stopping power, electron backscattering coefficient, down to more realistic scenarios, dosimetry in brachytherapy, again, calculation of those in hadron therapy, break peak simulation, or we have this test of internal breast dosimetry, where we compare the results of the simulation against experimental measurements performed with TLD detectors when this breast phantom, is being irradiated with the electrosynchrotron light source. We find that the best performance in this test was obtained with the option for electromagnetic physics constructor. Another test is this one for where the proton and carbon ion beams of with therapy energies are incident on a water phantom, and we calculated the break peak, and we compare the range at 82% distal fall off for both the protons and the carbon ions, and we find that for proton beams all the physics constructors agree with experimental uncertainty. In this case, we adopt only the binary cascade for hadronic physics, but we change only the electromagnetic physics constructor because the position of the break peak depends on that. Instead, for carbon ions, we found that the option 0 electromagnetic physics constructor is not accurate, but we expected that because that has been option 0 is more adequate for high energy physics applications and certainly not for medical physics. Option 4 and other physics constructors are more adequate. Now we are now doing the regression testing of the test with Geant4 10.5, 6, and 11 patch 1, but here we comment just on some significant changes because you can refer to the medical physics paper for already existing results. Well, we found an improvement in the electron backscattering test. We found that option 4 that demonstrated in previous regression testing to be accurate, the results remained satisfactory. That is very good because we don't want that the results, let's say, get worse. But what we noticed is that we found that option 3 electromagnetic physics constructor showed a significant improvement when in the modeling of the electron scattering coefficient, and because it's a multiple scattering has been improved. So I would like to show this test because it's a new one that is not documented in the paper on medical physics. The yields of positron emitting nuclei that are originated with therapeutic carbon ion beams incident on different phantom materials are calculated with Geant4 and compared to experimental measurements obtained at the IMAC Heavy Ion Treatment Facility at QST in Chiba, Japan. And these tests were done for incident carbon ions and oxygen ions. On the right, you can see the results. We calculated the normalized mean squared error considering all the radiation yields of the positron, the yields of the positron emitting nuclei, and we use these physical quantities, the normalized mean squared error, to quantify the agreements. And we found out that the binary ion cascade among the three fragmentation model provide the best agreement against experimental measurements. I would like to mention that the ICL we tested, but this hadronic physics list is more adequate for neutron spallation. For neutron spallation is not really meant to be used in heavy ion therapy, but we decide anyway to see how it behaves for completeness. And we found out also, you see, we repeated the test for different versions of Geant4, and we found out that the best model was in Geant4 10.5. Then, unfortunately, we had some we had less nice results with other Geant4 releases, but then with 10.6, 10.7 and 11, the situation got is getting better. Next step, we want to include we want to extend the test to Geant4 DNA. We want to add test for small field X-ray dosimetry. Here you can see a plot on the right that is a dose profile in water obtained with the Geant4 simulation and experimental measurements performed with the CyberKnife, fixed cone and iris. We want to include this test in the benchmarking, and we want to add more tests on hadronic physics and add tests in use case scenarios that are not currently covered, like nuclear medicine. Let me finally comment on some advances that we have in the advanced examples for medical physics. You had to know that we have 27 examples in total, and 13 are dedicated in medical physics, spanning from brachytherapy to proton therapy to positron emission tomography. So this one, the depth of interaction enabled whole body PET scanner, is one of the most recent examples that have been introduced and models the open PET of NIRS Japan. And yes, you can see the image is reconstructed. We have a new advanced example, the models, the ICRP 110 Phantom. We added the agreement to release this code, and the user can calculate the dose in each individual voxel of the Phantom or integrated over the entire organs. For the next release of Geant4, we'd like to include the ICRP publication 145 Phantoms. Yes, this is our next goal. In conclusion, Geant4 is in continuous development to improve it and extend its functionality. The physics component is regularly benchmarked to monitor its evolution, also in medical physics within the G4 Med project. And we have this constant effort to provide new examples to facilitate the use of Geant4 in the medical physics community. I think that in the past 20 years, Geant4 improved a lot for medical physics, thanks also to the synergy between the Geant4 collaboration and the medical physics community. That's all from me. Thank you very much.
Thank you so much, Susanna. Can I please ask you kindly to stop sharing your screen?
I will try, yes.
Excellent. I am really amazed how many advances have been achieved in Geant4, and I'm pleased to see all the ICRP phantoms, which will be wonderful for dosimetric calculations. Questions are being posted into the Q&A box of the Zoom meeting, but I will ask all the questions at the end of the session. I will share the screen again. And I would like to introduce, it's a great honor to introduce our second speaker for tonight, Professor Sebastien Incerti, who will give us an overview of the Geant4 DNA project. And Sebastien is Director of Research at the National Center for Scientific Research and the National Institute of Nuclear and Particle Physics in France. And he is involved in the development of the open source Geant4 Monte Carlo toolkit for the simulations of particle matter interactions. He has spent a lot of time to look at application areas, including medical physics, space sciences, and in particular for Geant4 DNA project, for which he has been the spokesperson since 2008. Over to you, Sebastien.
Thank you so much, Eva. Good afternoon, everyone. And thank you again to your colleagues for inviting us and giving us this opportunity to give a talk on Geant4 DNA. So let me share my slides. Do you see the slides?
Yes.
Perfect. So it's a great pleasure to present this talk on the Monte Carlo simulation of biological damage induced by ionizing radiation at the DNA scale. This will be an overview of the Geant4 DNA project. I'm, of course, representing the efforts of the whole Geant4 DNA collaboration. So this is the contents of the talk. I'll introduce briefly the context of this project, and I'll present you the different stages of, one second, I have a small problem here, the different stages, sorry, for the simulation of interactions of radiation with biological targets. So I'll describe the physical stage, then the physical, chemical, and chemical stages. I'll also introduce geometrical models of biological targets and how we calculate the induction of biological damage. And I'll show you where to find more information. Every time you see these green rectangles, you can click on the links and you will access interesting papers. So the context first, as you know, we are all undergoing exposure to ionizing radiation, from chronic exposure, from radon, medical exams, ground exposure, and so on. It's above 4.5 millisieverts per year in France. Some of us are undergoing more regular medical imaging, so they get higher doses. And above 100 millisieverts, we consider that there are long-term effects, which can become problematic, especially for those of you who will be lucky enough to go to space. And for example, on the moon, if you stay 1 year, you will get 200 times more dose than on the Earth, of course. And this is becoming, of course, much more problematic in the case of radiotherapy treatments, where we try to reach very high doses, 1000 millisieverts per minute, to kill the tumor cells. So today there are major open questions which remain in radiation protection. What are the biological effects of low doses of ionizing radiation? And what are the risks associated with high doses, in particular regarding the healthy tissues around the tumors? So Melenders et al. In 2009 were stating that a major challenge lies in providing a sound mechanistic understanding of low-dose radiation carcinogenesis. And on our side, we try to follow the in silico approach to try to bring answers or elements. So in silico, what does that mean? What does this mean? Sorry. In Geant4 DNA, we follow the Monte Carlo approach, which can reproduce, as you know, with accuracy, the stochastic nature of particle material interactions. Today, many Monte Carlo codes already exist and can be used for radiobiology to simulate track structures in the biological medium at the molecular scale, mainly in liquid water. For example, the golden standard is PARTRAC. There are other codes like TRACS, RETRACS, RITRACS, Kerbeck, MC4V, and so on. You can find a nice review on of these codes in this paper here. They include physics, physicochemistry processes, descriptions of biological targets down to the DNA size, DNA and chromosome damage simulation features, and also repair mechanism. But unfortunately, they are designed for very specific applications They are not always accessible. You cannot access the source code or mainly just the executable code. They are not adapted to recent operating systems. You cannot extend them. And after a while, they usually die. And NICU in '98 was suggesting to make something available to the community through the internet. So we decided to follow the Geant4 approach that Susanna very nicely introduced. So the idea first was to try to, of course, deliver something usable in full open access for the community. The problem is that Geant4 by default cannot really be used to simulate what's happening at the DNA scale. It has indeed strong limitations which prevent its usage. And what are these limitations? First of all, it adopts a condensed history approach. There is no step-by-step transport on small distances, which is a key requirement when you are doing micro or nano dosimetry. There is a nice paper here, which was written in collaboration with Susanna on this topic. There is a limited low energy limit applicability of electromagnetic physics models in Geant4, for example, the Livermore model. They have a very limited accuracy below 250 eV, and they cannot go below 10 EVs, let's say. And for the Penelope models, well, they are not accurate below 1 keV, so they should be used with care. There are no descriptions of target molecular properties. It's liquid water as the sum H2 plus O, and DNA nucleotides are not described, and other materials are needed when you are working at that scale. And of course, Geant4 only describes physical particle-material interactions, and probably you know that at the cellular scale, physical interactions are not the dominant process for DNA damage induction. So that's why Geant4 DNA came out. The idea was really to extend Geant4 for the simulation of interactions of radiation with biological systems in the context of space exploration mission. Indeed, the idea of Geant4 DNA was proposed in 2001 by Petteri Nieminen from the European Space Agency. It's a C++ extension which is fully integrated in Geant4, fully included. So we follow the releases of Geant4 because we are in Geant4, 2 releases per year. In 2007, we released the first physics models dedicated to Geant4 DNA. In 2008, we decided to add extensions toward chemistry and geometries. We released the first feature to simulate the chemical stage in 2001-04. Since 2001-07, we provide new alternative features for the simulation of chemistry as well as geometrical targets. And since in 2022, we will soon release full simulation chains, allowing you to simulate early DNA damage. And this is done in collaboration, was done in collaboration with a few theoreticians, whom we thank here. So let's look first at how Geant4 DNA proceeds to simulate DNA damage. So we follow a classical approach. First, just after irradiation at t equals 0 here, starts the physical stage where you will model step by step all the physical interactions of the incoming and the secondary ionizing radiation with the biological medium approximated as liquid water. This will lead to excited and ionized water molecules, as well as the creation of solvated electrons, which attach to water molecules. And these species will enter what we call the physico-chemical and chemical stages, where we will simulate the production of radical species, their diffusion in the medium, and their mutual chemical interactions. And if you combine both stages with geometrical models of targets from DNA to cells, well, then you will be able to simulate direct DNA damage at very early times, and then indirect DNA damage up to 1 microsecond. After that, you can use analytical model to describe the repair of such indirect or direct DNA damage estimations. So let's look first at the physical stage in green here, at the very first one. So this is a nice illustration that is showing you what Geant4 DNA is doing. On the left-hand side and the right-hand side, you can see a single 20 MeV carbon track simulated with Geant4 standard physics. That's the blue line here. And the red lines are the secondary electrons. And in the center here, we use exclusively Geant4 DNA. So you see that we have many more yellow points. These are all the physical interactions that occur in liquid water and that are all simulated by Geant4 DNA. So you are more accurate in terms of energy deposition or space resolution, but of course slower because you need more time to simulate accurately what's going on. So in Geant4 DNA, to simulate such interactions, we provide many models. So I'm not going to read everything here, but you see that in pink, we treat electrons, protons, hydrogen atoms, alpha particles and their charged states, a few ions, the ones that are dominant in the cosmic spectrum, and photons. And in cyan here, you see the physical processes, elastic scattering, ionization, electronic excitation, vibrational excitation, dissociative attachment, and so on. And the names in green here are the models on which these processes are based to describe the process itself. That is the deviation of the incident particle, its energy loss, the creation of secondary particles, and so on. So it's a lot of models and processes, and this took some time to create all of these. And you see they were the subjects of many theses here that started in 2007 and are described in those papers here. This is an illustration, for example, of the cross-sections that Geant4 DNA provides. This is elastic scattering, the cross-section, total cross-section as a function of incident energy for electrons. So all the lines are the different alternative models we have in Geant4 DNA. And the points, the symbols here are experimental data. We have the same for electronic excitation, ionization, and the sum of inelastic cross-sections. Unfortunately, no data exists in the liquid water phase, so we have to rely on data in the gas phase or in the ice phase. And the model lies in between. There is no strict way to validate all these models. This is why we propose several alternatives, the different curves that you see here. So to ease their usage, we provide 3 physics constructors which contain all these models, so you don't have to worry about them. You simply call one of these 3 constructors, and Geant4 DNA will treat the electron interactions according to all these models that are assembled here in those constructors. They have different energy ranges, up to 1 MeV, 10 keV, 250 keV, depending on the models that are used. And of course, they can treat other particles like protons, alpha particles, and so on, for which we do not have currently alternative models. And also, we are able to treat other materials like solid gold for nanoparticle studies or DNA precursors. We did some efforts in trying to validate or verify, not say validate, the physical quantities that Geant4 DNA simulates. So they are listed here on this left column. They are described in these 2 papers here, and I'm simply focusing on 2 of them, range and stopping power, because they are the most known. So for example, this is a plot showing you the range of electrons, protons, and alphas in liquid water as a function of their energy. The points are ICRU non-zero recommendations, and the colored lines here are Geant4 DNA results for electrons or for protons and alphas. So there is a reasonable good agreement from ICRU, 9.0 less than 10%, below down to 10 keV, I would say. And here for the stopping power, you see that the ICRU recommendations stop at 1 keV. So below that, we have no way to fully verify the models. So this is why we provide 3 alternatives. So they did, all of them, of course, they look reasonable, but we cannot tell which one is the most accurate, since there is no strong recommendation on that. Now we switch to the second stage, physical, chemical, and chemical stage. So that's what we see here. We start first with the physical chemical stage, which in that stage occurs at very short times, up to 10 to the minus 10 seconds after irradiation. And in that stage, this is where you break or you excite your water molecules. And these water molecules, they will either dissociate if they have been ionized or if they have attached some electrons close to them, or they may relax or dissociate if they have been excited or underwent electron hole recombination. So you see the states of the different water molecules here and what the channels, the dissociation channels that they may undergo. And in Geant4 DNA, we provide 2 schemes describing these dissociations or relaxation. And both of them can be used in Geant4 DNA. The first one is the oldest one that was delivered in 2001-4. And the second one is a recent update that we performed in 2020, if I remember well. Then the chemical stage starts from 10 to the minus 12 seconds up to 1 microsecond. So in Geant4 DNA, we provide 2 alternative approaches. The first one, the oldest one, but accurate, is the step-by-step approach, which simulates the Brownian transport of molecules. After the physical stage, you can see here a single electron track with the yellow points being ionization and excitations. Then you will create all the molecular species that result from the de-excitation, dissociation, or relaxation of the water molecules. And all these radicals, they will propagate in the medium and attack your DNA. So here we, in this step-by-step approach, we represent chemical species by point objects, which will diffuse in the medium. And the medium is supposed to be fully continuous. That's the blue here. Chemical reactions are controlled by diffusion. Two reactants interact when their separation distance is smaller than the reaction radius, which is calculated from the rate constant of the chemical reaction. We handle 7 species, 9 chemical reactions. So this is very accurate. You can track all radicals, but it is very slow and requires a lot of memory. Alternatively, we provide since last year the independent reaction time approach, which is much faster. In that case, it's an iterative process where the approximation of independent pairs is used. It calculates the reaction times between all possible pairs of reactive species and considers them as isolated. Then the reactions, they occur one by one, starting with the pairs having the shortest reaction time. So it's no longer necessary to diffuse all the molecular species, so it's much faster and requires much less memory. Here we handle 15 species, 72 chemical reactions. And a new version has been recently added since January to be compatible with geometries. All this is described in these papers. So we provide 4 chemistry constructors, like 3 for physics. All of them have their own specifications. The first one is the oldest one. Then it has been reviewed with a new set of parameters for the description of the physical and chemical stages in 2019. We added the reactions with DNA components. This is needed for the simulation of DNA damage induction. And the last one, option 3, includes the IRT approach. And this work with the IRT inclusion was done in collaboration with the Topaz and Bio collaboration in the United States. So this is an example of simulation of the chemistry stage, let's say. These are radiochemical yields, that is the concentration of a molecular species as a function of time. So G is here, and this is the time. For different species, these are, for example, hydroxyl radicals. And in blue and in pink, you have 2 Geant4 DNA chemistry constructors. The default one in blue is the oldest one, and the newest one in red, option 3, using IRT. So the same for all these molecular species, and you can see that we have a reasonable agreement with experimental data from the literature. And this is done using a new example that is called Chem6 that's available in Geant4 DNA. Now, if we look at the modeling of geometrical targets, well, we started a few years ago with an interface to use this fantastic protein data bank, which contains many text files describing the 3D structures of molecules, proteins, nucleic acids, and so on. So for example, here, this is an example of dodecamer. You have a description of all the position of all the atoms in that macromolecule. And here, this one is a tetranucleosome. So what was done was to really develop a dedicated example called PDB4 DNA. It's a C++ library that will read these PDB files, create bounding boxes around the geometries, and then allows you to search for closest atom from a given point. This is useful when you want to calculate the energy deposition in a specific volume of your molecule. And it features 3 granularities: barycenters of nucleotides, an atomistic description, and barycenters of nucleotide components. This is what you can see here for the DNA on these 3 schemes. And it's also a Geant4 DNA example, which will indeed code that geometry, place it in liquid water, and then you can shoot particles to calculate DNA damage, direct only, I mean, single strand breaks and double strand breaks. That was the first try a few years ago. Then a major step was made by Nathaniel Lampe in 2017, when he developed a full integral approach, including the IRT chemistry, to simulate DNA damage in a bacterium, so E. coli in this situation, in this development. So it's a combination of physics, chemistry, IRT, plus a geometry of the bacterium to predict induction of SSB and DSB, direct and non-direct damage, and it's fully controlled by Geant4 user interface commands. So very easy to use. It contains, you see, a few millions of base pairs. Another step forward was made by during the PhD of Sylvain Mélan. So this time, this geometrical model described a human cell fibroblast nucleus. So the idea is really to code and using Geant4 capabilities, the chromatin fibers completely available in the full genome. So you can see it amounts for 6.4 gigabase pairs. So this was done during his PhD, and the construction of this nucleus is based on an external software that is called DNA Fabric that was developed by Sylvain and that is available on this website. Another interesting or funny development was developed by the group of Munk Bata and Lagva and Dr. Belov in Dugda and in National University of Mongolia. They developed a simple geometrical models of neuron cells in order to simulate physical and chemical interactions of ions with neurons. This is important for modeling of DNA damage to the central nervous system. So once you have these geometrical models, how can you calculate DNA damage? So there are many parameters to optimize to describe the direct induction of DNA damage and the non-direct DNA damage induction. You have to select your physics constructor, the volume of energy scoring for the direct DNA damage, and the probability of single-strand break induction. This is what is shown here. And for non-direct damage induction, you have to select your chemistry constructor, the probability of non-direct SSB induction. So typically we consider only OH being able to attack your DNA backbone. The distance from DNA to kill radicals, this is required to simulate scavenging in cells. Histones also in cells, human cells, are considered as full scavengers usually. You can also play with the radiolysis maximum time steps, like a movie, and also the radiolysis end time, up to 1 microsecond, for example. So when you do that and you use the previous geometrical models I've shown you, so for example, using the fibroblast model of Sylvain Mélan, you can reproduce the number of DSBs as a function of LET for proton irradiation. So the simulation results are the green crosses and experiments are all these other symbols. So a nice agreement. And these are simulation results in blue compared to literature simulations. So the parameters selected here are described in this small rectangle. If you use the other approach developed by Nathaniel Lumpy, this work was continued to extend it to a full cell nucleus model. This is described here, containing also 6.4 gigabase pairs of DNA. This was done by Dosatsu Sakata when he was working with Susanna in Wollongong. And doing the same, you can also simulate DSBs as a function of LET with different parameters that you can also test. And the good news is that this chain called molecular DNA will be a new example that will be released in 3 weeks. So where can you find more information if you are interested in Geant4 DNA? Of course, we have a website here where you can find all our publications, 28 examples, PhD theses, links to tutorials, and our virtual machine. We have a Twitter account if you are interested to get recent news. I'm not going to read that, but these are the 28 examples that show you how to use Geant4 DNA physics, chemistry for radiolysis simulations, geometries, and so on. And also we provide a Geant4 virtual machine that is something easy to download, uncompress, and use. It will simulate a virtual Rocky Linux PC on your local machine. It's totally free, and it contains fully Geant4 DNA, and other tools like Root, which are usually used during the examples to display data. So I thank you very much for your attention. So, and a special thank you, of course, to all the theoreticians and Monte Carlo experts who have helped us. These are on the left, this is the list of our main contributors. You see that Susanna is really highlighted here because we have been collaborating together for so many years. We are 61 collaboration members in 2022. You see them all over the world except Africa, but hopefully we will have soon new collaborators. And above all, we thank our users. And of course, if you are using our developments, please cite our 4 collaboration papers. Thank you very much for your attention.
Thank you so much, Sebastien, for a fantastic overview of Geant4 DNA. Excellent talk. May I please ask you to stop sharing your screen? Thank you. And we'll start asking some questions that were typed into Q&A. Susanna, there used to be a Geant4 derivative called GATE for medical applications. Is this still useful, or do you recommend to work directly in Geant4?
Okay, no, GATE is still continue to be developed and used. So I think it really depends on the specific user, what he or she wants to use. The Gate, Gate, for example, it doesn't run in multi-threaded modes and relies often on previous Geant4 releases. So it doesn't not use the latest release of Geant4. While
it's not updated properly.
Yes, it's always a little bit in delay.
Behind.
Yes, and I think that the Geant4, I strongly suggest Geant4 if you want to run in multi-threaded modes. Also, if you have different applications that you'd like to use Geant4 for. Gate, for example, is more used in nuclear medicine. So it really depends on the user or on what you really need to do with Geant4, and also if you'd like to learn to some C++ to improve your computing skills or not. So
you mentioned some verification, and do you make use of AAPM report 195 test cases when validating new versions of Geant4? I'm not sure whether you are familiar with that AAPM report.
PM report, we don't use that.
You don't use it, yeah. Thank you. Can Geant4 be used to make a hybrid PET Compton with the current version?
Yes.
Yes, okay, fantastic.
It should be. I mean, if it doesn't, let me know, please.
Excellent. Sebastien, a user is simulating the behavior of free radicals in magnetic field, but Geant4 DNA has no model to simulate these effects of free radicals. Is there any development here?
Yes, in fact, you can, I guess so. I didn't test myself, but normally for the physics, that should be okay. For the chemistry, the only person or Geant4 DNA collaboration member who has tried is a very good colleague of Susanna and myself. His name is Dr. Sakata. He's based in Japan. He has been working on that topic, combining modeling of radiolysis inside a magnetic field. And we may provide you his email address to get full details. Or currently, there are no immediate plans to deliver that in Geant4 DNA. But of course, if at some point technically it's feasible, we will add this. So please send us an email, and we will put you in contact with Dosatsu Sakata.
Excellent. ICRP 145 Phantom has been using Geant4 recently, and due to the very fine detail of the Phantom, several kernel approximations had to be implemented to reduce simulation time. Are there any suggestions for Geant4 users who want to use these Phantoms but do not have access to HPC facilities, so high program computer facilities?
Yes, I mean, I suggest to use biasing techniques. I mean, this is what we do, for example, in our group with ICRP 145 FED. I totally understand the problem, and what they can help is biasing plus HPC facility, but at least the biasing.
Sebastien, can Geant4 DNA be used for fast neutron therapy?
So the problem, we don't provide any models for the transport of neutron now in Geant4 DNA, but what you could do, you could simulate the transport of neutrons using Geant4, which is accurate for that. And then you will create some protons, which will create electrons and so on. And you create a phase space file starting from these protons and electrons, and then you run Geant4 DNA with them. So there is just an intermediate step where you have to extract exactly. So in practice, it should be doable.
It's possible. You just need to create the source of neutrons. Yes.
Exactly. So use Geant4 for that, and
then you can go on from that. Is it feasible to model a clinical linear accelerator with Geant4 and then use a validated clinical beam for an experiment using Geant4 DNA? So I think this is like a two-stage process: create a beam in Geant4, but then do radiobiological simulations in Geant4 DNA with this beam model.
Probably, yes.
I don't see why not.
Yes, exactly. What users should understand is that Geant4 is really a toolkit like Geant4 DNA. So you really can adapt it to your own needs. So it's very flexible. It's a bit complex because you have to code, but once you know how to code, it's very, very powerful.
But that's exactly the benefit of it. You have the back door open and you can do with it what you want.
Exactly.
Rather than systems where you can pull down menus and you only select options and you can't do nothing more than that. Yeah,
absolutely.
Are chemical constructor and molecular geometry provided in your mentioned the website? So can people get access?
So first of all, you access them through the code. Regarding the chemistry constructor, you may find details about them in the recent publications. And we are currently undergoing a process of preparing a review of all the chemistry content. So that.
So when people download the software, they will have access to all those
absolutely.
examples.
Yes,
and all
absolutely.
Those
everything is there.
Yes. How do you incorporate SSB or DSB repair in your model?
So it's currently we are funded by the European Space Agency, and next year there will be a release of these models. So it's technically doable. We have published already papers on that. So the models are ready. They just need to be interfaced with the chains that will be out by the end of the year. So it's a matter of months, I would say. So, but of course you can read the papers. Everything is explained, and you can already see how this is done technically. So. There's nothing mysterious, and it's the models are based from published models. So it's we have simply coded them and add them to the output of the early DNA damage.
People would like to compare Geant4 and Topaz, what they should use. Do you have a suggestion?
I mean, in theory, I hope the Geant4 and Topaz give the same results because the Topaz relies on Geant4.
Yeah, exactly.
So I expect that they will provide the same results. Again, the Topaz provides is a platform that allows a easier use of Geant4 for the medical physics community. Again, the user should do an informed decision on which platform to use. Gate, Gamos, or Topaz, or use directly Geant4. Okay.
So if someone is doing research in proton therapy, should they use Geant4 or Geant4 DNA? I presume that depends on the research question.
Absolutely, you're totally right.
Whether you may be calculating a point dosimetry or looking at the cellular damage.
If you want to simulate hydroxyl radicals, you cannot with Geant4. So you have to use Geant4 DNA. If it's really dosimetry or millimeter scale simulations, you have to use Geant4, not Geant4 DNA. It's too slow. There's no point. It really depends on exactly what you want to study.
Can you use Geant4 for high LET particles? Susanna?
Yes,
you show your carbon 12
absolutely.
examples.
Yeah, there is no.
Yes. So how can Geant4 simulation with DNA damage judge its accuracy? Basically, this is what we ask our students as well. How did you verify your results?
Okay, so we need very nice and clean experimental results that are reproducible, of course. The only experimental values can really be used for validation. Otherwise, if it's comparison to other codes, you will say we verify Geant4 DNA. And if you don't have nothing, if you don't have anything, then you say, it's plausible. So
with error bars.
Exactly. But so you see, for example, for electrons transport below 1 keV in liquid water, beyond ICRU 90, we have nothing. So we don't know. We have these 3 sets of models because we don't know what is the most accurate. And it's only physics.
It will give you a range of maybe plausible values.
Yeah, exactly. So that's why an important point is that we never claim that we are the most accurate, but we remain the door open. If one day a theoretician or an experimentalist has more accurate models, is welcome to contact us, and so we can add the model to Geant4.
So you have active collaborations also with the experimentalists to share their experimental data with?
So for now, it's mainly on the chemistry side and a little bit on the biology side. Yes. And
chemistry experiments are terribly difficult.
Absolutely. And so we have 2 groups in France doing that, but requires time, specific expertise that we don't have. We are not from
and it's actually that measurement on a very short time scale.
Absolutely.
Where that you don't have equipment or technology to measure the free radicals under 1 microsecond.
It's a total domain of expertise, and you know.
Yeah.
But what was very surprising is that when you hear these experts, they tell you that we don't have any open access software. So we need them, and they are happy because they can have this platform that can do so much. Geant4 DNA.
So do you also validate against other codes like ParTrack, RightTrax, or whatever else is there?
We compare with, yes, you will see in the papers that we try as much as possible to add their results on our plots. Of course, we cannot run these codes because they are proprietary codes. We cannot access them. So we really rely on what they have published. That's it. But I can tell you that usually it's a friendly competition because people are happy to help. I mean, and we understand that they have their own needs. So
you have no idea. I will have to finish here. How fantastic it is to have something like Geant4, where it's constantly being developed. It's for free, and you have a wonderful community. And students can sign up to the user group and post their problem online to get the answers and everything. Where I know, and this is, for example, an example from nuclear medicine, where a company would like to maybe charge up to 2,000 euros a month for modeling of a single isotope.
Okay, really?
Yes. So I think Geant4 collaboration is just amazing and absolutely fantastic. I have to really finish here in the interest of time. So thank you, Sebastien and Susanna, for spending time with us. I will share the screen one more time just to advertise the topic for tomorrow. I hope our colleagues will be still able to join us tomorrow and on the Friday night, where tomorrow our Vice President, Professor John Damilakis of IOMP, will be moderating a seminar presented by Professor Hilda Bosmans. John, would you like to add any words, please?
No. See you all tomorrow, same time.
Thank you, everyone. Thank you, Susanna.
Thank you.
Sebastien.
Thank you.
Thank you.
Bye.
Have a nice day.
Bye-bye.
Bye.